Ah, there he is. Sorry, I saw you posted a comment already. You already jumped on that. You're already here to learn. Yeah, I'll talk a little bit more about that later. But the long story short is my daughter's arm ended up being broken. So yay! Later this afternoon, I have to travel to Freehold to take her to an orthopedist. Um, After our live stream yesterday morning, the rest of my day was spent on the phone, getting in contact with the pediatrician, setting up a live stream visit with the doctor, going to Health Village Imaging to get an X-ray, trying to make 1,000 different appointments in 1,000 different places. Yay! But regardless, I'll probably post something to that effect a little bit later. Yeah, it does. I'll probably post something later on Twitter to that effect. But yeah, she has an appointment today at 3:45 in Freehold, and it won't affect my teaching or my work schedule today, thankfully. Um, yeah, and we'll figure it out. But I'm gonna give people an opportunity to kind of climb in because I said 10 o'clock and it's only 9:58. I just posted the link on Google Classroom. Man, why can't I not think of things today? And yeah, we'll figure that thing out. In the meantime, I'm gonna go get a couple things. I got my book ready. I got my paper ready. Ooh, where's the paper from yesterday? I had a paper from yesterday. Did I lose it? Nope, there it is. I got it. There we go. I'm pretty much going to pick up where we left off yesterday with this. Yes, we will. But I'll pick up with that in a little bit. I'm just going to give people an opportunity to get into the chat, talk amongst yourselves. And yeah, I'll be back in a few minutes. I'm going to get a snack. All right. When I post something in Google Classroom, do you guys get like an alert or an email or something to that effect? Or will you only know about it if you log on to Google Classroom? I asked two questions and you said yeah. So I don't know which one. Oh, you get notifications. Is that something that you have to like click or does like that happen automatically for everybody? Ah, okay. That makes sense then. Why the same kids are always like turning stuff in very quickly. And why others have not. There we go. I'm looking at Google Classroom right now. Who's turned in what? All right. I'm going to get started approximately 10:05. I think that's kind of my aim, because I said 10, and I want to give people an opportunity to kind of get in, if they haven't gotten to the link yet or gotten to their whatever lately. I don't know. I found a game earlier. I'm going to see if I can paste the link to that game. I'm teaching discrete math, and in discrete math, we're learning something called... Oh, he already did it. We're doing something called Euler paths and circuits. Holy crap, that was pretty good. Good for him. I gave them an assignment, and a kid has already done the assignment. I gotta find the link to the game. I'm gonna post it here. And it's a kid's game, but... There it is. Boom. It's a kid's game, but it uses properties of Euler paths and circuits that we've been learning in discrete math to do it. And I don't know, this kid already did his assignment and he got a pretty good score. So you should check it out. Or you have to like enable Flash or some junk like that on your computer. That was a fun game. Then I'm gonna get started. People might join in the middle. That's okay. But we'll see how this thing goes. I would just like to kind of get this lesson moving along, rolling along, so we can kind of get this thing going. So, where we left off yesterday, I had given the title to this section, and I had written f of x equals 1 over x. Now, as a reminder, you can type this into a graphing calculator. Oh, excuse me, a graphing calculator if you have one. Otherwise, you can go into Desmos. I'm going to post a link to that in a moment. But you can go to Desmos. You can sign in using your school Gmail account. There's the link right there, desmos.com/calculator. And you can type in exactly what I have right here. F of x equals 1 over x. And if you do that, you should see the exact function that I need you to see. And I'm just going to take a look at that just so people can, oh no, get a reference for that. I typed in the total wrong thing into Desmos. There we go. Equals 1 divided by x. Boom. And that weird squiggly line that you see, that is what we're going to be dealing with today. Now, I'm just going to put it into my y equals key, my graphing calculator right here. Chapow. And this weird image is what you see. See if I can zoom in a little bit. Am I allowed to zoom? Yeah, I can zoom in a little bit. Look at me. Now, this image on the regular TI-83 calculator does not look this nice. You're going to see my calculator has a better way of displaying this thing, a much better way of displaying this thing than the regular TI-83 calculators do. In fact, on the TI-83 calculators, a lot of the time there's this weird squiggle right in the middle. Let me remove my axes real quick, just to give you an idea as to what this thing really, really does look like. Now, I don't have a dry erase marker. Oh, wait. No, that's a Crayola marker. I don't have a dry erase marker on me, otherwise I'd draw directly on my calculator. But the thing that you should realize is that this portion of the graph right here does extend down forever. And this portion of the graph does extend up forever. This is a really weird function. This is called the reciprocal function. I want to give you an idea as to what it looks like on paper, and then we can get a much better idea as to what the heck this thing is doing. So, 1 divided by x. Just as a side note, these two curves do not touch each other. These two curves do not touch each other, number 1. Number 2, they go on forever. There's a weird, weird thing going on here. So, first and foremost, the thing that you got to realize about this, and I'm putting this into my notes for you, but this graph has, for the lack of a better term, let's just say 2 asymptotes. Now, we learned, I know you don't like it, we learned in exponentials that there was a horizontal asymptote. It was an invisible barrier that the graph approaches but never crosses. Now, for this chapter, there's a similar definition to it. Oh, I'm still zoomed in. Thank you. See, this is why I need a live chat. Otherwise, can you imagine a set of notes where like people are like, just what the heck's going on? There we go. Much better. Anyway. But in exponentials, we learned about asymptotes, and that gave us a very particular definition. In this chapter, they're going to have a similar definition, but I'm going to have to slightly change one of them. We'll deal with that when the time comes. So let me just draw the prototype of this graph right here. So here's your x and y axis. This graph has 2 asymptotes, a vertical one at x equals 0, and a horizontal one at y equals 0. Remember the general concept of a Hoy-Vux. H-O-Y, horizontal line. Y is the only letter in the equation. Vux, V-U-X, vertical line. X is the only variable in the equation. Technically speaking, and I'm going to embellish this just a little bit so you can see it, but there is a vertical asymptote directly on top of that axis, and there is a horizontal asymptote directly on top of this axis. And again, I'm embellishing them just a little bit so you can see them. The general concept behind them is that the graph, for the most part, approaches but never crosses. The horizontal one may have a slightly different definition a little bit later on, but we'll deal with that when the time comes. Now, in my calculator, I'm just going to get a few ordered pairs off of this thing to the left, and to the right. I'd like to create a little table of values here. So let's see. I'm not going to get every single one of these points. That'd be weird. But let's just go with like -2, -0.5, -1, -1. Now if you notice at 0, there's an error. We'll deal with that error in a moment. But then at 1, there's 1. At 2, there's 0.5. We'll deal with that error in a moment. I'll come back to that. Let's plot these. -2, -0.5, -1, -1. 1, 1, and 2.5. Now, looking at this graph, and you can see it curving back in here, and again, you can see it on Desmos as well, you can see generally what this thing is supposed to do. So, this thing is curving downward forever like that. And it's flatlining going to the left. Same thing right here. It's flatlining going to the right. And as it approaches that vertical asymptote, it's going to curve up and avoid it forever. That's what this thing does. This is the reciprocal graph. Typically, when we do rational functions, they'll look something like this. They'll look like a couple of curves that don't touch each other, that are just curving off into space somewhere. It seemingly looks like a very, very basic function, 1 over x. But it gives you something that is just weird, to say the least, what this thing does. Meh. Now, to go back to the calculator real quick, there is a reason why you got an error for 0. There's a reason for that. If you took that x value of 0, and you don't have to type this, you don't have to write anything, I just want you to think about it. If you took a 0 and plugged it into this function, you would have 1 divided by 0. And that can't happen. That cannot happen. It's impossible. As a result, error. Can't do it. In fact, that asymptote, that vertical asymptote, is right in the middle of the graph, right at x equals 0. The graph can never exist on a vertical asymptote. The graph can never, ever exist on a vertical asymptote. It's not a part of the domain. Now that's it. Let's talk about domain. Now, range, we'll deal with range another time. But let's talk domain for this particular function. If we're talking domain, we're talking about all of the possible inputs. If we're talking about domain, we're talking about all of the x values that you are allowed to plug into the function. Now, in this instance, you are not allowed to plug in a 0. You get an error. Can't do it. This graph extends left forever. It extends right forever. The only x value you are not allowed to put in is 0. 0 is the only number that is not a part of the domain. As a result, this is what the domain would be. Looks terrible. It looks terrible. But it's what it is. That is exactly what the domain is. What that domain is trying to say is it's trying to say all real numbers except 0. Except using the notation that we have typically used. You can't really just write out that sentence, all real numbers except 0, but this is a much more elegant way of writing it. It's trying to say negative infinity to infinity. But what it's really saying is negative infinity up to 0, but not including 0. Don't include 0. Unioned with 0 to infinity, but again, don't include 0. It's saying all numbers but 0. Crazy. The range is a different story when it comes to these types of functions. The range isn't always obvious because the horizontal asymptote does little wacky things later on. So I'm only really focused on what the domain is for this. We'll deal with the range another time. Let's look at another example, and then I'm going to give you a general function in a moment. There we go. Boom. So let's look at, there we go. Example. And this, I'm getting these examples directly from the textbook because I like what they look like. F of x equals 3 over 2x plus 5. Now, take a moment. If you have a graphing calculator, type that into your graphing calculator. If you don't have a graphing calculator, type it into Desmos. You can get rid of the original function that you typed into Desmos. I'm going to do the same thing in my calculator. Or my calculator and in Desmos. But I'm going to do 1 divided by, if you're going to type it into Desmos, I'm sorry, it's not 1, it's 3. 3 divided by. If you're going to type it into Desmos, make sure you get that 2x plus 5 completely in the denominator. Completely in the denominator. And the way that you would do that on the graphing calculator, if you can see that here, the way that you would do that on the graphing calculator, 3 divided by, parentheses, 2x plus 5. You got to make sure that you put parentheses around the bottom of that fraction. Absolutely yes. Now, if I graph that thing here, I get this. Fair warning. If you're using a TI-83, there's going to be this weird, wacky line trying to connect the two curves. That weird, wacky line right in the middle should not be there if you're using a TI-83. In the TI-83 graphing calculator, it does not know how to properly handle vertical asymptotes. It doesn't. And since the TI-83 doesn't know how to properly handle that asymptote, it fills it in with a little squiggle. And it looks like it should be there, but it's not. It is absolutely not there. It's a vertical asymptote. Asymptotes are invisible barriers. We indicate them with dotted lines, yes, but it should not actually be a part of this graph. Now, there are several things I could do in order to graph this thing. First, I could go to the table of values, but, oh, look at all those numbers, fantastic. I'll copy some of those down in a moment. But the most important thing for you is to be able to properly identify what the horizontal and the vertical asymptote is. Now, from the graph, and of course I would suggest graphing it at some point, definitely yes, but from the graph, you can hopefully see, oh, it looks like y equals 0. Absolutely yes. For these functions, for the most part, y equals 0 is, for the most part, going to be the horizontal asymptote. For these reciprocal functions, they are going to get a bit more complex as time goes on, and I'm going to show you that. Some of these more basic reciprocal functions are just going to have a linear in the bottom of the fraction. 2x plus 5 is a linear function. If it's not linear, we'll have to deal with that. 1 over x was linear in the bottom. So, for the most part, and I'm going to write these definitions down a little bit later, the horizontal asymptote is going to be y equals 0 for this problem. That's going to change for the next one. We'll deal with that later. But the vertical asymptote, how you determine the vertical asymptote is trying to figure out what value of x you are not allowed to put into the function. What value of x you're not allowed to put in the function. Kyle, where'd you go? You said I'm back? I didn't even know you left. Sorry, I was in my own little world. Anyway. Here's my question to you. Not just to Kyle, but to everybody watching at this point. I know there's only a couple people watching in the chat right now, but that's perfectly fine. You're making rice. It's pretty good. Is it white rice or is it yellow rice? My mom makes amazing. Yeah, my mom makes amazing arroz con pollo with sazon. It's a spice from Goya. It's amazing. Anyway, enough of my Puerto Rican heritage. Back to this. The question then becomes, what are we not allowed to plug in? What are we not allowed to put in for x? Well, the only number that we would not be allowed to put in for x is whatever number causes the bottom of this fraction to be 0. If the bottom of that fraction were 0, boom, we have a number that we're not allowed to plug in. So here's how you figure that out. Set the bottom of that fraction equal to 0. If you set the bottom of that fraction equal to 0 and then solve, you are going to find the x value that you're not allowed to plug in. Let's just see what happens. Clearly, I just subtract the 5, then I divide by 2, and I get a negative 2.5. Or negative 5 over 2, but I'm going to do the decimal because I want to show you where it is. That is the vertical asymptote. Just writing those little there. Now, we'll deal with that on the graph in a moment. Let's go to this. And yes, I'll try to remember to zoom back out when I'm done. If I hit trace and try to type in a negative 2.5, watch what happens when I hit enter. Look for the y value. It's gone. The reason why it's gone is because that is where that asymptote is occurring. Again, a vertical asymptote, the graph is going to avoid a vertical asymptote at all costs. If you ever see a graph that looks like this, where it's trying to avoid an x value, you better believe that that's a vertical asymptote. I'm going to remember to zoom back out. Sorry, I heard something. My daughter's fine. Just, okay. Anyway, back to this. So if I'm going to try and graph this thing, I'm also going to need a little table of values. But here's the deal now. When you make the table of values, you want to make sure that you get a few x values to the left of that number and to the right of that number, the number that I'm pointing to. You need to make sure that you get a few ordered pairs that are to the left of the vertical asymptote and to the right of the vertical asymptote. We need to know where that vertical asymptote is. So, if I'm going to my graphing calculator, negative 2.5 is where that asymptote occurs. So, I'm going to get a couple numbers to the left and a couple numbers to the right. I'm going to get negative 4, negative 1, negative 3, negative 3. The asymptote would occur there. That's where the error would occur. I don't need to write that. Negative 2, 3, and negative 1, 1. They're not always going to be kind of symmetric like that. They're almost like reflections of each other across a diagonal, but again, that's not the point of this. Now I'm going to go ahead and try and graph this. Now, like I said, I knew what the horizontal asymptote was, and I'm going to give you the definition of the horizontal in a little bit. But basically, there we go. It's right on top of that axis. Now, the vertical asymptote, like we said, was at negative 2.5. So, right at negative 2.5, there is a vertical asymptote. That's a terrible vertical line, but I'm going to pretend it's vertical. You're going to get that vertical line. Now I'm going to plot some points. Points that I got directly from the graphing calculator. Negative 4, negative 1. Negative 3, negative 3. Now again, notice the vertical asymptote. I'm going to draw that curve in a minute. negative 2, positive 3, negative 1, positive 1. Note where the asymptotes are. For these problems in 8.3 for basic reciprocal functions, they are going to avoid the asymptotes at all costs. That asymptote extends. Same thing right here, and same thing down here. When we graph these functions, or I'm sorry, let me rephrase, when you graph these functions, you're going to need to be very careful to make sure that you indicate where everything is. I'm going to ask for you to indicate what the asymptotes are. I'm going to ask for a table of values that you can get directly from your graphing calculator or even from Desmos. You can get a table of values in Desmos. Maybe I should do a tutorial on that one day. But then I'm going to expect smooth curves and asymptotes where they're supposed to be. It's going to be phenomenal. Let me give you a few definitions. Oh, you know what? Let me do the domain first. Let me do the domain first, and then I'll give you a few definitions. The domain for this problem, well, negative infinity up to the asymptote with a parentheses because it will never touch the asymptote, unioned with negative 2.5 to infinity. That's what that thing does. Let me show you something else in the graphing calculator. Check this out real quick. I'm going to zoom in. I'll remember to zoom back out in a little bit. There we go. I have that function typed into my y equals k. Now, if we did negative 3, clearly we get negative 3 back because that we dealt with that right there. I'm pointing to the table of values. Negative 3, negative 3. Cool. What if I did negative 2.9, negative 2.8, negative 2.7, negative 2.6? Notice what's happening to the y value. They're getting bigger in the negative direction. Now, I can't do negative 2.5. If I did negative 2.5, it's not going to work. I'll do that and then I'll come back. See, you can't divide by 0. Negative 2.5 is where the vertical asymptote occurs. So I can't do negative 2.5. So let me do negative 2.51, negative 2.501, negative 2.5001. Look what's happening to the y values. They're getting bigger and bigger and bigger in the negative direction. I'm getting closer and closer and closer to negative 2.5, but I'm not at negative 2.5. I can do that again, and again, and again, and again, and again. I'm getting closer and closer and closer to negative 2.5, and I'm getting a larger and larger and larger negative number. If you go back to the graph, zoom back out there. Woo. If you go back to the graph, we're getting closer and closer and closer to negative 2.5, and it's getting larger and larger and larger in the negative direction. Now, if you look again my calculator one more time, I'm never going to get to negative 2.5. I'm never going to get there, unfortunately. Oh no. My calculator at some point gives up and says, hey, divide by 0. But I'm just getting closer and closer and closer to a concept known as negative infinity. But I'll never get there. I'll never reach negative infinity. Because of that, your calculator says, can't get there, unfortunately. I'm going to try and zoom back out. Woo! That's good. There we go. Let me give you some definitions. I love this thing. These are the funnest graphs ever. Once we get past the basics, there'll be some, in my opinion, funner graphs. But we'll see. So this is the basic reciprocal function. You should be scared, Kyle, because you know what's coming back? You know what's back? You don't know what's back. I know what's back. Your favorite two letters in the whole world. Yep, that's right. H and K. I haven't laughed like that in a while. I need to laugh like that more often. Hold on. Hold on. Here we go. There it is. There it is. There it is. H and K. H and K do the same exact thing they have always done. H will shift the graph horizontally. K will shift the graph vertically. How can I stop? I can't stop. I won't stop. I told you guys back in September that H and K would be haunting your dreams, but they do the exact same thing. This A does the exact same thing it has always done. The exact same thing. This A will actually flip the graph vertically if we wanted it to. This graph might dilate the graph vertically or horizontally depending on what that number is, but I'm not going to worry about that. I'm going to worry about the flips per se. So let me go back to this real quick. Check this out. So I had this graph, which was the one we just graphed. 3 over 2x plus 5. Heresy. Whatever. Now watch this. I'm going to put in a negative symbol. I'm just going to throw in a little negative symbol right there, just for the fun of it. I'm going to make it a negative 3 on top. Graph. Look what it did. It flipped the graph vertically. It flipped the graph vertically. That's what this thing does. I'll show you something weird. When I was in high school, I'll zoom in a little bit. When I was in high school, I already knew everything, of course. So I decided to just play around with the graphing calculator. I would play around with the graphing calculator constantly just to see what it could do. And one of my favorite things to do was this. I would deal with these reciprocal functions. There we go. And you can actually put in 10 different functions into this graphing calculator. It's really phenomenal. Watch what happens when I graph it. I don't know. Sometimes you get bored with math and you just want to see how far you can take math. So that's the difference between me as a student versus most high school students. The idea was that yes, I was bored with it because I already knew how to do it, but I wanted to see how far I could take it. And I would always mess around with functions like this. This is the basic reciprocal function. I would make stuff like this in the calculator. It's awesome. It is awesome. But I digress. Here's the deal. You want to find your horizontal asymptote to this? You want to find your horizontal asymptote? Your horizontal asymptote, otherwise known as it's going to be y equals k, just like exponentials. It's the exact same thing. Oh no, Kyle, you reminded me again. I'm still zoomed in. Why do I forget that I'm lost in my own world? Anyway, your horizontal asymptote, otherwise known as is y equals k, just like exponentials. Well, your vertical asymptote, well, basically, here's your procedure. Oh, otherwise known as va. Set denominator equal to 0 and solve. Set your denominator equal to 0 and solve. It's not ha, it's ha. Anyway, But that's what we did before. You set your denominator equals 0, you solve, you find your vertical asymptote. You need to find exactly where that vertical asymptote is supposed to be. You have to. In order to graph these, you're going to identify what those asymptotes are. You're going to find a table of values, a couple points on each side of the va. You're going to a couple of points on each side of the va, the vertical asymptote. And you're going to draw that thing out. This is your procedure. And of course, you're going to identify your domain. Now, whatever your vertical asymptote ends up being, your domain should have the following structure, so to speak, for these basic reciprocal functions. Yeah. Whatever the vertical asymptote ends up being. And then you draw that thing out. Like I said, we can shift these things whichever direction we want with H and K and all that fun stuff. But these are the proper procedures for them. It's really phenomenal. Really, really phenomenal. Now, these are your basic ones. I want to talk about your non-basic ones. Your crazier ones, so to speak. They are scary. What's scary? The ones that I'm going to show you, or the one that I just showed you? I would like to know your opinion. Both. You haven't seen anything yet. You have not seen anything yet. Cow. Okay. Here we go. I want to take it a little bit farther. And again, I'm going to put timestamps in so you can come back and rewatch whatever you need to rewatch. Timestamps will be in the video probably this afternoon at some point. Actually, no, probably not this afternoon, but whatever. I don't care. This is going to be phenomenal. Oh my gosh, I'm so excited. What about non-basic reciprocal function? So here's what I want you to do. If you have a graphing calculator, or go to Desmos. See if I can paste that link one more time. There it is. You can go to Desmos. You can log in using your Barnegat School's email. I want you to put in the following function. F of x equals 3 over x squared minus 1. Take a moment. Type it into your graphing calculator if you have one. Type it into Desmos if you have Desmos open. Something a little bit more advanced than what we've done so far. I'm typing it in myself right now. Boom. Exactly, Kyle. What the hell is that? Oh, goodness. These are my favorite graphs in all of Algebra 2. Like, unbelievable. Like, my favorite topic to cover is exponentials. But my favorite graphs are these. Oh, man. The excitement level. Let me type it into my graphing calculator. Just in case you, the viewer, haven't typed it in or are unable to type it in or something. Is that a W or no? Where? Oh, wait. Is that a W or no? Right here? That says function. That says function. The graph. Oh, the graph. Let's just see what happens. I don't know. Let me zoom in. And I'll try to remember to zoom back out. Oh, there's one of my old Lost Thoughts people from like 10 years ago. That's fine, dude. You're totally fine. Lost was an interesting show up until the end. And now it holds a dark place in my heart. So, but that's a conversation for another day. Conversation for another day. Anywho's, it's back to this. 3 divided by x squared minus 1. Ha. Kyle, that's not a W. Here, let me get rid of these things right here. Let me get rid of the axes real quick. Chapow. These are 3 separate curves that are produced by one equation, is what this is. These are 3 separate curves produced by one equation. Oh, you typed it in wrong. Oh, maybe. Well, it should be this. 3 over x squared minus 1. We'll see what happens. Graph is a really weird thing. Now, a couple questions. Again, rhetorical. But the graph, as you move left to right, seemingly is avoiding some kind of barrier and then reappears down here. And then it is avoiding a different barrier and then reappears up here. Boom. This problem has 2 vertical asymptotes. This problem has 2 vertical asymptotes. Now, there is a definition that I am going to give you. Zoom back out, I know. Zoom back out, there we go. There is a definition that I am going to give you eventually. Come on, little thingy. There we go, much better. But for the sake of argument, you may not understand why this is at the moment, but your horizontal asymptote is y equals 0. Now your vertical asymptote. What I told you to do before for the basic reciprocal function was to take the denominator and set it equal to 0. You want to find your vertical asymptote? You take the denominator and set it equal to 0. You take the denominator and set it equal to 0. And now you got to solve. Now, what did we do in 8.1 and 8.2? What did we do with functions in 8.1 and 8.2? We were simplifying rational functions. We were simplifying them by multiplication division. We were simplifying them by addition subtraction. And there was a first step that we had to take. There was a first step that we had to take. We had to factor. You're going to do that again here. For this problem, if you were to factor x squared minus 1, which you can because, well, it's quadratic, and then solve, because I said set it equal to 0 and solve, you're going to get 2 numbers. X equals positive 1, x equals negative 1. You have 2 vertical asymptotes. 2 vertical asymptotes. Technically, you can have as many vertical asymptotes as you want. Hey, Kyle, you want to see something weird? Based on the statement that I just said? Okay. Kyle said sure. There we go. I'm about to show you a graph that has an infinite number of vertical asymptotes. You will be graphing something like that next year. If we do have a next year. I know, it is. It's fantastic. But this one has an infinite number. You're not doing that. You're doing something basic like this one. So, we need to do a few things. There's a procedure that we are going to follow. The procedure that we're going to follow will, number 1, identify your horizontal and vertical asymptotes. Then, I'm going to need a table of values. So, I'm going to go to my graphing calculator. And I'm going to go to my y equals key. You want to get a few numbers to the left. You want to get a few numbers to the right. Notice there's 2 errors in there. Oh my gosh. You don't have to write the errors. You don't have to write the errors. But I would like a few ordered pairs to the left and a few ordered pairs to the right of the errors. Now, if you notice, they only gave us 1 ordered pair in the middle. You don't want to graph... Whatever, you're going to graph it anyway. Too bad, Kyle. But these numbers came directly from the graphing calculator. So, I'm going to graph this sucker out. First, I'm going to need to put in my 2 asymptotes. That are the vertical ones, that is. Then, I'm going to need to put in my horizontal asymptote. There we go. If you notice, the asymptotes actually break up the graph into 6 sections. It's weird. It's so weird. But it's what this thing does. It's exactly what it does. I'll plot some points. Let's see. -3 and this itty-bitty number. -2 and 1. Now, again, from the calculator, I know that the curve is supposed to do something like that. It's going to avoid the vertical asymptote, and it's going to coast along and flatline going to the left. Now, the middle section is weird. You only have 1 ordered pair right there. Now, on the calculator, this is where you really need to either look at the calculator or look at Desmos, because you can see what that curve is doing there. The best that we can do is this. It's not always going to do that. It will not always do that. But according to our graph right here, it is what it does. How are we supposed to know? Well, you either have Desmos or you have your own calculator. Oh, happy day. 2, 1. 3 and itty-bitty change. Flat lines. Avoids the asymptote. That's what this graph does. Let's talk domain. The domain stretches left and right forever. But you have 2 vertical asymptotes where the graph is not allowed to exist. Because if the graph were to exist at +1, you get a 0 in the bottom. If the graph were to exist at -1, you get a 0 in the bottom of the fraction. You can't have that. Vertical asymptotes will occur when the denominator of the fraction equals 0. So, your domain, it's going to be a little weird here, but -infinity up to that -1, not including it, of course, unioned with -1 to 1, because it does exist in the middle, unioned with 1 to infinity. There are 3 sections to this graph. I love it so much. It's so phenomenal. These things. Now, again, these are one of the more basic ones as well. But there are some rules that I have to go over with you. I know you don't like it, Kyle. I know you don't like it. It's amazing, though. Let me give you some rules. Let's see here. What are the rules for graphing these? Rules for graphing rational functions. I want to make sure I list these out right. So, first, make sure function is a single fraction. Make sure that the function is a single fraction. Meaning, it's something like f of x equals some function divided by another function. If you have two fractions being added or subtracted together, that is what you have to do from 8.2. That is where you actually have to simplify them into a single fraction and then see what you can do from there, finding common denominators. I'll do another example like that in a little bit. Then you can determine vertical asymptotes. Now again, VA, I'm abbreviating. You could determine vertical asymptotes by setting denominator equal to 0 and solving. You could determine your horizontal asymptote, your ha, and I'm going to show you how all of this works. I'm going to come back to this page a lot. By taking leading terms, I should say, on top and bottom, and simplifying. I'm going to show you what that looks like. It's actually a lot simpler than it seems. You could even determine x-intercepts by setting numerator equal to 0 and solving. I'm going to be doing all of that with the following example. So you need to make sure you have a single fraction, f of x equals a of x over b of x. Two functions. Now, I'm going to put something here that I haven't put in a while. Bask in the glory of the star. Make sure it's simplified. Make sure it's simplified. That fraction. One more little note here, because this is going to be amazing. This is going to fry your little brains, and I'm going to love it so much. If anything canceled out from simplifying, you have a hole. Oh, this is going to be amazing. I'm going to show you how to deal with that hole in a little bit. Literally, there could be holes in your graph. Like a legitimate, like, hole, open circle hole. It's going to be amazing. I'm so pumped. But in all honesty, these are the nuts and bolts. If you can remember each of these bullet points, you can graph any of these things. One little extra little side note. So I can rub on my paper and I pass. No. The horizontal asymptote. And Kyle, let me see what you think about this. Listen to the following statement. The horizontal asymptote may not always be horizontal. This is a weird statement. Let me repeat what I just said. The horizontal asymptote in this set of problems may not always be horizontal. Now, what I'm going to do, I'm going to do an example with you. And I'm going to walk you through each of these bullet points. And I'm going to show you exactly how they play. It's going to be phenomenal. So let's start. That's a decent one. Do I want to do that one? No, I don't want to do that one. I don't want to do that one. I want to do one that's going to do what I want it to do. Ooh. Now that's a good one. Okay. That's a good one. I got one. I got to get a paper. So excited. I'm going to bring this paper back in a moment. Haha. You don't even know which one it is, Kyle. Example. Anyway. F of x equals x plus 1 over x squared plus x minus 2. Wait, does that work? I need to make sure it works. No, that one's good. That one works. That's fine. That's perfectly fine. That one works. We'll start it off with this one. Now, for the sake of argument, you could type this in to the y equals key in the calculator or into Desmos just to get a look, just to see what the heck it looks like. I'll zoom in and I'll zoom back out. Hey, Sky's here. Sky, have you been here the whole time? Kyle, I want you to panic at that one. It looks amazing. Oh, okay. I got you. You can always go back and watch the first part of the video. Timestamps will be in the description later. Kyle, this graph is amazing. It does exactly what I wanted it to do. So. Zoom back out. That's right. Oh, let me zoom back out. There we go. Good, 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 good. Oh, my daughter. Did she just knock on the door with her bad arm? Oh, no. No, Ellie, don't do that. Oh, okay. So, just so you know what just happened in the last minute, my daughter came to the bedroom door and knocked and called for, yeah, there's the child. My daughter called for me and she knocked on the door, Daddy, and then she knocked on the door, and then all of a sudden I hear, ow, and I'm like, no. Kyle knows about it. Sky, I don't know if you knew about it, but yesterday we were doing the live stream and I had to shut it down because my daughter, during the live stream, fell off my son's bunk bed and broke her arm. And yeah, the rest of my day from there on was calling doctors and trying to figure out appointments and figure out when we're going to get x-rays and all that fun stuff. So, yay. No, I know. But yeah, so we have an appointment with an orthopedist this afternoon. So after I'm done working today, I'm going to go head out there and we'll figure this thing out. But anyway, I'm sorry. Back to this. The thing that's the bane of Kyle's existence, this graph. So let's walk through the procedures. First and foremost, your first step will always be to factor. Always. The top of the fraction doesn't factor. The bottom of the fraction does, but it factors into an x plus 2 and an x minus 1. Nothing simplifies. Nothing cancels out. Let me put a little note here. Because nothing cancels, no holes. There's the possibility of holes. We'll deal with that in the future. But because nothing canceled, there are no holes. So that takes care of one of our bullet points. There are, what, 1, 2, 3, 4, 5. There are 5 bullet points. Number one, we did already have it as a single fraction, and we did try to simplify, so that I already took care of that bullet point as well. You have to make sure it's a single fraction, and you have to make sure it's simplified. Because nothing canceled, no holes. Now let's deal with our vertical asymptotes. The definition of vertical asymptotes, you have to set the denominator equal to 0. And then solve. Right here, boom, denominator equal to 0. Now mind you, notice I'm using the factored form. The denominator equal to 0, and you solve, you get 2 vertical asymptotes. 2 vertical asymptotes. Let's deal with the horizontal asymptote. The ha! For the horizontal asymptote, according to that paper, it said take the leading terms on the top and bottom and simplify. Well, look at my leading terms. I have an x and an x squared. If I took y equals x over x squared and simplified, I'd get 1 over x. What is the horizontal asymptote of 1 over x? Oh, I don't know. Maybe it just so happens to be the very first function that we did today, which had a horizontal asymptote at y equals 0. Yes. Yes, it is. Y equals 0 is that horizontal asymptote. Let's figure out our x-intercepts. You take the numerator, the top of the fraction, set it equal to 0, and solve. You get x-intercepts. Let me just walk you through exactly what just happened here, because we're about to graph this thing, and it's going to be amazing. So, first and foremost, let me just walk you through the procedures, the rules. Make sure the function is a single fraction. Make sure it's simplified. You can make sure it's simplified by factoring and seeing if anything cancels. Next, you determine the vertical asymptote by setting the denominator equal to 0 and solving. You determine the horizontal asymptote by taking the leading terms on the top and bottom and simplifying. You determine the x-intercept by setting the numerator equal to 0 and solving. And if anything canceled out from that step up there, you have a hole. And I'll show you in a future example where that hole may end up being. So, what did we do? For this problem, we had a single fraction, but in order to see if it simplifies, you need to factor. Nothing canceled. Because nothing canceled, we don't have any holes. Then, we took the denominator, the factored denominator, set it equal to 0, and solved. You got 2 vertical asymptotes. Then, we took the leading term on the top and bottom of the fraction, the leading term, and simplified them to get 1 over x, which the very first example we did, the reciprocal function, has a horizontal asymptote at y equals 0. Next, we took the numerator, the top of the fraction, set it equal to 0 in order to find any x-intercepts, which we do at -1. It is not a guarantee that you'll have any x-intercepts. It's not a guarantee. We'll deal with those in future examples. So, get a little table of values action going on here. I only need a couple points to the left, a couple points to the right of each of the vertical asymptotes. -4, -0.3, -3, -0.5, -1, 0, 0, -0.5, 2, and positive 0.75, 3, and 0.4. This should work. Again, the vertical asymptotes, there was one at -2, and there was one at +1. In fact, this may be helpful to actually put those dotted lines into the table of values so you can see, oh crap, that's where the vertical asymptotes actually were. This is just a little aside that I just came up with right now, because it makes me $1 million. Just a million, nothing more than that. Anyway, let's graph this sucker out. If I were to graph this thing out, first, let me put my vertical asymptotes in. There's one at positive 1. And there is one at negative 2. There we go. I have a horizontal asymptote at y equals 0. I have an x-intercept. And you can see it right there. There's the x-intercept, actually. x-int. It's in my table of values, but we found it already over here. It's not always going to be a whole number. But my x-intercept is right there. That's strange. It's right on top of the horizontal asymptote. I know I'm going to talk about that in a moment. I'll talk about that in a moment. Negative 4, negative 0.3, negative 3, negative 0.5. According to the graph that I saw, this thing would curve downwards like that, and it would curve outwards like that. 0, negative 0.5. According to the graph that I saw, and again, you could see this on Desmos, you can see this on your graphing calculator if you had one, but that's what the middle of the function did. 2.75 and 3 at 0.4, according to the graph, it did something like that. That's this function. That is exactly what this function does and how it acts. Now, big question. Did you see that the graph went through my horizontal asymptote? The graph went through the horizontal asymptote. For these functions, they technically are allowed to do that because the definition of a horizontal asymptote actually indicates the end behavior. I'm going to write that actually down here. The horizontal asymptote, the ha, indicates end behavior. It indicates end behavior. It indicates what the graph is supposed to do way far to the left and way far to the right. Forever. We did a little end behavior when it came to polynomial functions. Whether they both went up, both went down, weird. But the horizontal asymptote is actually going to indicate end behavior in this case. It's weird. Let's talk domain. Again, the range is a little bit weirder to deal with because the range here is technically everything, but I'm not going to deal with that. The range would be negative infinity up to the asymptote, unioned with negative 2 to positive 1, up to the asymptote, unioned with, I ran out of room, 1 to infinity. That would be the domain of this particular function. I love it so much. Kyle, tell me you don't love this stuff. He's going to tell me he doesn't love this stuff. Anyway. You should... Well, okay. You know what, though? You said slightly scared. Slightly scared means that you're not, like, fully terrified. Slightly scared is like, oh, I don't know about this movie. Some junk like that. And then you might end up enjoying it. Let's try another one. I take that back. I'm scared. I need to be... Okay, if you say so. If you say so. So, let's try another one. Let's try one where stuff does end up canceling out. Oh, that's a good one. No, don't be terrified. Let's Excuse me. Let's do another example. F of x equals... Kyle, you don't even know which one I'm doing yet. Shut up, Kyle. I want to make sure this works out quite nicely. X cubed plus x squared minus 6x divided by again, give me a second. I want to make sure that this works out the way that I want it to. There it is. Okay. X squared minus x minus 12. Got it. I just came up with that example off the top of my head. Oh, happy day. This function has it all. This function is phenomenal. Step one. Well, actually, you know what? Even before step one, let's just see what it looks like. Let's just see what it looks like, Kyle. I know that this is going to work out the way that I want it to. I know that it is. It's going to be phenomenal. I'm just double checking to make sure that I typed it in correctly. You're going to like it in the end, Kyle. Don't worry. Graph. That is phenomenal. Oh my goodness. Yup. Oh man, this is gonna be great or terrible at the same time. I'm gonna look at the table of values here. It's gonna be so great. Okay, let's take it a piece at a time. Yeah, it falls. It does. You thought like, oh, it looks fine, and then it totally turned directions on you. Okay. Now, for the sake of argument, this is the last problem I'm going to do today. This is the last problem I'm going to do today, and then I'm going to call it a day. I'm going to get some lunch. But this is an amazing problem to finish on. First, yes, it's a single fraction, but you need to make sure that you simplify. You need to make sure that you simplify. And in order to make sure that anything simplifies, you need to factor. For the sake of argument, I know exactly what this factors into. You're going to have to take out a greatest common factor of x at the top of the function, and then the remaining quadratic factors into x plus 3, x minus 2. That's stuff that we've been doing for a long time. The bottom of the fraction factors into x minus 4, x plus 3. Now, this is going to be amazing. It's going to be so amazing. This function, you can see that something cancels. You can see that something cancels. Oh my goodness. It's going to be so great. The x plus 3's cancel each other out. As a result, x plus 3 canceled. So, set that equal to 0. There is a hole. There is a hole at negative 3. We're going to deal with that hole a little bit later on. But this goes back to that bullet point. If anything cancels out, or if anything canceled out from simplifying, you have a hole. There's going to be a hole at negative 3, and we'll deal with that when we get there. We'll deal with that when we get there. Let's walk through the steps, though. Let's walk through what we're supposed to do. First, let's find a vertical asymptote. You want to find a vertical asymptote? Set the denominator equal to 0. Now, I don't have to worry about the x plus 3 because it canceled out. And since it canceled out, I already took care of it over here. So the only thing that I have to set equal to 0 is x minus 4. I solve there. I have a vertical asymptote at x equals 4. Done there. Now, now I gotta find a horizontal asymptote. Hold on one second. My son is calling me. I think he's looking for Ludicolo. Hold on one second. James, are you okay, bud? Oh, you okay? Do you need something? The double stroller. Okay, hold on, hold on. Okay, let me help you out here. Okay. First, let me walk. Going for a walk. Okay. I locked the cat door and I opened the garage door. He's getting the double stroller. Do you need anything? Okay. Yeah. Go that way, babe. Okay. Okay. Okay, I'm back. Sorry about that. Oh goodness. Ah. Wait, what was that? I gotta worry about holes now. Fun. Scaring me like it. Sorry about that. My wife and my wife is taking the kids out on a walk, and she's putting them in the double stroller, and they needed help getting the double stroller out. Again, timestamps. I'll put the timestamps in, and I'll say, hey guys, remember that time? Timestamps. You can skip this part, and you can skip that silence. Anyway, I'm back. Is all that matters. Back to this. Yes, there are holes, but they're not too bad. I'll show you how to deal with them later. Ooh, my daughter's yelling right now. Oh, poor kid. Actually, let me show you what this hole does. I'll zoom in right here. The hole is supposed to be at -3. Now look at this. -1. Look where it's blinking at -1. It's an ordered pair. It works. Let's go to -2. See it blinking at -2. Now, there doesn't seem to be anything wrong at -3. Let's go to -2.5. There doesn't seem to be anything wrong at -2.5 or -2.8 or -2.9. There doesn't seem to be anything wrong with that. There's nothing wrong with it. Until we try to get to -3. The second that we get to -3, look at the y value. It's not there. Because there's a hole in the graph. The calculator won't tell you that. If you try to go to the table of values, it'll just say at -3. It's phenomenal. I love this stuff so much. But, like I said, I have personally simplified the process as to how you are going to graph it. Why does the line not like -3? Well, Kyle, do you know, it's not that it doesn't like it. It's not that it doesn't like it. Kyle, I want you to pay close attention to this. Let's pretend for a moment that we never canceled out this x plus 3. Let's pretend we never canceled it out. And we're back here in the quadratic. If you plugged in a -3 into this quadratic, it would result in a 0 in the bottom of the fraction, which cannot happen. That can't happen. It's not allowed to happen. You're not allowed to divide by 0. Thankfully, it canceled out. Poof. But because of that, the original function still has -3 as something that can't happen. It can't happen. But since it canceled out, there is no vertical asymptote there. There's no vertical asymptote at x equals -3 because it canceled. But as a result, you have to make a concession, and that concession is a hole. Oh, I love this stuff so much. Math is amazing. Anyway, back to this. Horizontal asymptote. According to the horizontal asymptote rule that I gave you, I said determine the horizontal asymptote by taking the leading terms on the top and the bottom and simplifying. So let's do that. The leading terms were x cubed over x squared. Math is only scary because you don't know it yet. Hey, Kyle, let me ask you a question, Kyle. Have you ever read the book, The Monster at the End of the Book? Have you ever read that? I've read it too many times. You should look at it. It's a Sesame Street book. It's phenomenal. You'll understand what I'm talking about when you read it. But anyway, if I were to simplify x cubed over x squared, guess what happens? You just get an x. You just get an x. Ladies and gentlemen, your horizontal asymptote is actually not horizontal. Is what they call a slant asymptote. It's a good read. It's a short. It's a kid's book. It's a kid's book. It's about lovable furry old Grover. But anyway, because it's y equals x, I actually have a slant asymptote. If you noticed right here, the slant that occurs. Remember, the horizontal asymptote is actually indicating the end behavior of the graph. The end behavior. It's phenomenal. And it's a slant. I'm going to show you how to deal with that. Don't you worry. Now, let's deal with the x-intercepts. X-intercepts. Well, remember, x plus 3 canceled out. You take the top of the fraction. You set it equal to 0. You get 2 x-intercepts. You get 2 x-intercepts. One at 0 and one at 2. Now, let me just walk through my bullet points, make sure I did everything. Make sure that the function is a single fraction. Check. Simplify. Make sure it's simplified. Check. Determine vertical asymptote by setting the denominator equal to 0. Check. Determine the horizontal asymptote by taking the leading terms, top and bottom, and simplifying. Check. Find the x-intercept by setting the numerator equal to 0 and solving. Check. If anything canceled out from simplifying, you have a hole. Check. I have all the information I need. I need a table of values now. Now for a table of values, again, you want to get ordered pairs to the left and to the right of your vertical asymptotes. Now, in this case, I'm actually also going to get an ordered pair to the left of my hole as well. You get a little glare there. There you go, much better. You get a glare. Now, there's a hole at -3. I'm just going to pull a dotted line there. -2, -1.3, -1, -0.6, 0, 0. Scroll down a bit. There's the other error. 1 and then 0.3. And then 2 comma 0 and 3 comma -3. And the other, there we go. Oh, that's right. I have more ordered pairs to get. Let's see what happens. Oh, crap. Got a couple ordered pairs there that I didn't get. Let me put a little addendum right here. 5, 15, 6, and 12. We'll deal with that. That's strange. Those numbers are large. I wonder what's going to happen. Huh. Let's see what happens. Now, since I'm getting numbers that large, perhaps I should try to do something like this. There we go. Because I'm going to have to go up to 15. Let's put our vertical asymptote. 1, 2, 3, 4. Vertical asymptote. Now here's the deal. I'll come back to the hole in a minute. I'll come back to that conversation. I will explain the existence of holes in this problem after I graph this stuff out. Now, the horizontal asymptote is a slant, and it's slanted at y equals x. That's what that asymptote does. I understand. This is a difficult topic to visualize in general. If I actually had Desmos on the screen, I would be able to show you guys a bit more, but unfortunately, there would be a huge lag in the live stream if I were to change this up and actually show you Desmos on the screen right now. It's frustrating. I don't have the best of computers. But I'll do my best to see what we can do. If I had a tablet, I could actually put like the tablet here. Anyway, I can't use my phone because my phone is my webcam. You know, if you plug a hole for X, then it will turn. Oh, that's actually a good way of putting it, Kyle. But you know what? Again, let's come back to that. Let's finish this problem up. 2 and 0, they are my x-intercepts. There's a hole at -3. I'll deal with that hole in a little bit. -4, -3. -2, -1.3. -1, -0.6. Did I put that in the right spot? Let me double check my numbers here. -4, -3. -2, -1.3. -1. Yeah. Yeah, I must have graphed that weird. Actually, oh, that goes right there. That's why. Okay, that makes more sense. Cool. And then 1 and 0.3. There we go. Now, and 3 and -3. From the calculator, I could see the first part of my graph doing this. Now, if you notice, going to the left, the end behavior of the graph. The end behavior of the graph is going to resemble that slant asymptote. The end behavior of the graph is going to resemble that slant asymptote. Now, I'm going to deal with the hole in a minute. But then going to the right, it's going to avoid that vertical asymptote. There's a hole at -3. Right there. There's a hole. I'll deal with that hole in a moment. Finishing the other side of the graph, though, I got to go up to 15. 2, 3, 4, 5. That's not going to work. 6, 7, 8, 9, 10. Maybe it will. 11, 12, 13, 14, 15. Oh, that's terrible. 5, 15 is all the way up here. 6, 12, 14, 13, 12 is right here. Now, you can't see it on your graphing calculator. You can't see it. I'm going to actually readjust my window right now so you can see it. But I'm going to readjust this so it's up to 20. And I'm going to readjust. No, that's probably fine. Yeah, here we go. So here's the first part of my graph. As always, there's the other part of my graph. There's the other part of my graph in the top right corner. Now, according to this, there should be ordered pairs to the right of this thing, to the right of this vertical asymptote. That's what it does. If we ever go back to school and take a test on this, I will make a literal hole where the hole is. Sure, by all means. Anyway, yeah, by all means. But that's what this graph does. See, originally, you may not have been able to see anything to the right of that asymptote. You may just think, oh, that's what it is. Yeah, oh, happy day. But everything that I've told you, you find out where the vertical asymptotes are. You find ordered pairs to the left and to the right of that vertical asymptote. Since the vertical asymptote was at x equals +4, you needed to find ordered pairs to the right of it. And because those ordered pairs existed, you had to realize that there was a top right portion to this graph. Now, in Desmos, you can actually zoom out a little bit, I believe. Yeah, you could totally zoom out in Desmos, and you can see exactly where that thing is. And I'm going to suggest that, like, if you can't see the whole thing, zoom out in Desmos. Now, going back to Sky's question, because this was the last example I was doing today. Sky, your question about holes. Holes are strange. The general idea, so these problems make more than one function. No, this is all one function with multiple curves. This is all one function with multiple curves. It's really awesome. In fact, let me back up a little bit to the previous example. This is the previous example we did. One function, 3 curves. It's all one equation, though. It's all one equation. But the procedure is very much the same. Let's look. Where's the other one that I did? Oh, here we go. Here's another function. 3 curves, 1 equation. Phenomenal. So going back to holes real quick, though. The original function, this is the original function all the way up here. And in the original function, if there is a number that causes the denominator to be 0, you get an error. If I go to my y equals key, or not my y equals key, if I go to my table of values for this problem, there is an error at -3, and there is an error at +4. There are 2 errors. But what do those errors do? If you graphed it, -3 is about right here. It doesn't seem like there's anything going on here. It doesn't seem like there's anything crazy. But at +4, there clearly is a visual vertical asymptote. Clearly a visual vertical asymptote. So how do we determine that on paper? How we determine that on paper comes down to your factoring skills. Now, yes, actually, let me fix this just a little bit. There we go, good. On paper, if you were to plug in a -3 or a +4 into this function, if you were to do that, you would get a 0 in the denominator, which causes those errors. But the question then becomes, what type of error is it? According to everything that we've been doing, you are to factor as your first step. Oh, that's a little, there you go, much better. You are to factor, that first graph is terrifying, I know, but you are to factor as your first step. And if you were to factor as your first step, you can see that the x plus 3's cancel each other out. Now, according to our rules, and let me go back to the rules real quick. These are the rules that I wrote down before. These are the rules for graphing rational functions. Bottom bullet point. If anything canceled out from simplifying, you have a hole. Now, I know. But if anything cancels, you have to automatically identify that as a hole. The general idea is that if anything is in the bottom of that function, it's going to be a vertical asymptote. But since the x plus 3, poof, popped away, it created a hole in the graph. If I were to, and I'll zoom back in real quick, here we go. If I were to go to -2.5, -2.6, -2.7, -2.8, you can see that the y values exist. -2.9, -2.99, -2.9999, -2.99999. It exists. But the second that you step over into -3, you fall into that hole. The graph does not exist at that point. It doesn't exist at that point. But at the same time, because it canceled out from simplifying, it is not a vertical asymptote. It is not a vertical asymptote. It's a really weird concept, but that's what we have here. We have to assume the simplified form. It's very strange. It's very strange. Just as a side note for the domain, you have to take the whole into account because the graph doesn't exist at the whole. So the domain, I'll write the domain down here. The domain for this function would be negative infinity up to the whole, union with this up to the vertical asymptote, union with 4 up to infinity. It does keep going forever. I love this chapter. Kyle, I know you hate this chapter. Or you don't like this chapter. And Sky, I know you said you were terrified by some of the problems that you saw. But this is the first full lesson that you've ever seen on graphing these things. It is a little scary. It's supposed to be. How do you learn to do anything? Kyle, let me give you a metaphor. Let me give you a metaphor right now. You ready? You ready for my metaphor? Tell me you're ready. Come on. Okay, he's ready. Mathematics, it's like climbing a tree. It's climbing a tree. Imagine a forest of trees, and each tree represents a different branch of mathematics. There's the algebra tree, there's the geometry tree, there's the trigonometry tree, there's the calculus tree, there's the statistics tree, and they're all next to each other, and some of their branches cross over with each other. You can be in the algebra tree, and then you could jump over into the geometry tree. You could be in the geometry tree and jump over into the trigonometry tree, or jump over to the calculus tree. But now think about what you're literally doing in that metaphor. You're in a tree, and you're jumping from branch to branch. That is a scary notion. It is. You have to be comfortable with your surroundings. You have to be comfortable and able to climb up that tree in the first place. And then brave enough to actually think that you could jump from branch to branch to branch. It is a scary concept. This stuff does not come easy to people. It doesn't. Oh, yes. Sky, you weren't here earlier for the domain conversation, but that little U just reads as the word union. The domain is the list of all possible inputs. The domain is the list of all numbers that you could plug in to the function. In this original function, excuse me, in this original function, you were not allowed to plug in a positive 4 or a negative 3 because they would cause the denominators to be 0. As a result, as I travel left to right, well, this graph goes left forever, but it goes left forever up to the whole, which you're not allowed to do. You're not allowed to plug in that negative 3. Then it goes from the whole up to the vertical asymptote, which you're not allowed to plug in a positive 4. And then it goes from the vertical asymptote off to infinity. The domain is just the list of all possible numbers you're allowed to plug in. Strange, I know. I once read an article in college that talked about how they wanted students to skip all of the basic stuff and go straight to some of the harder stuff using calculators and online tools. And they talked about how they described it as being a tree. And they're like, well, adding, subtracting, multiplying, dividing, those are things that, some of the basic stuff, graphing lines, some of the basic stuff, students have a tough time grasping that. And then they hate doing math after that. So what if we gave them a ladder to get up into the branches, and they can use the calculator for every calculation, and they never have to do any of that math in their heads? And I thought to myself, that's dumb, because what happens if you climb that tree and then the ladder falls down? You never learned how to get up. You just climbed a ladder, and now you're stuck in a tree. That's scary. Only solution, jump out, break your arm. And I brought it all full circle. Back to my daughter breaking her arm. Thanks for reminding me. Anyway, I'm going to call it a lesson here. I mean, I'm probably going to put the timestamp in saying that there's a life lesson at some point. But I'll put the timestamps in later today at some point. I am going to assign you guys an assessment on 8.1 and 8.2 next week. This lesson is 8.3 and 8.4, and we need to spend more time on this. We will. I knew we had to spend more time on it. I know that this is just an introductory thing, and I will have more live stream going next week, going over various problems with you. We'll deal with that when the time comes. In the meantime, like I said, I am going to assign something probably Monday. That's going to be some kind of an assessment that you guys are going to do on simplifying these things. So we'll deal with that when the time comes. Anyway, that's it for me. Also, just as a side note, Kyle, I know you like to jump in my live streams, but I'm having another live stream for AP Stat later today. That is completely up to you whether or not you do that. It's completely up to you whether or not you want to do that, but we are going to be going over various topics that you may or yeah, you'll join probably, and I thank you for that because you'll be giving me the likes and the minutes viewed on these things. So, but yeah, I'll probably be back on later today for that. Like, share, subscribe, click that notification bell. I'm a sign off, and I will see you guys another time.